And I don't know why the book doesn't introduce this one nicely, but they should introduce this one. It's an important notion called eigenspace, right? So eigenspace, of course, the book doesn't introduce notation, so I have to introduce it like this. So there's a map between T, abstract vector space. It doesn't have to be finite dimensional. I don't know if you notice it. The definition of eigenvalue and eigenvector does not require finite dimensionality. So here's the vector space going to vector space itself. Did you notice that also the notion of eigenvalue doesn't make sense if it's not going from V to V. It is like V is going to lambda V, so must be back in the V, right? So we only talk about eigenvalues of things only inside endomorphism of a V. We don't think about T is coming from LVW and eigenvector. It makes no sense. It has to go back to itself so that lambda V makes sense. All right? So eigenvalue, you know the definition of eigenvalues, right? And eigenvectors. So that you studied it. So I'm going to introduce let lambda be just a number in your field. Not necessarily eigenvalues, just any number in your field. It's a real number, it could be real, it could be complex numbers. And then I'm going to define eigenspace E lambda is not standard notation. I just have to make up like this. Eigenspace is by definition is a collection of all the vectors in the V such that if you send it along the T, what happens? Lambda V. That is called eigenspace. All right? First of all, why is that a subspace? It's a subset, right? Then you have to show why is this a subspace. It's a subspace. At least, do you see that it contains always at least one element? What is that one element that this one contains? All subspaces contains this element, 0, right? So 0 vector is going to 0, so no matter what your lambda is going to be 0 vector, right? So it has 0, close under addition, close under scalar multiplication. That you have to show. It's not hard if you just follow this definition. This is called subspace is called eigenspace. All right? So in your intuition, what is this E0? This is eigenspace for value 0, right? So lambda is going to be what? T and V. It's going to be 0. That's a 0 go here, right? V equals 0. Isn't that right? So what is the name for this guy? It's null of T. Isn't that right? It's null of T. So I don't know if you saw this or not. Null of T is really eigenspaces of eigenvalue 0. All right? Eigenvalue 0 is the space of the null space. All right. How about E1? Is a V, V, T of V, 1 times V, right? Is a V. So any vector that is fixed under, you know what I'm saying, right? So this is eigenspace. You can, for anything, you can consider E lambda. But often this is trivial, right? This is a case for almost all lambda you're going to consider in your field, right? Only very special. Those are called, if it is non-zero, non-trivial, and it's called eigenvalue, right? So let me phrase it this way. If E lambda is not trivial, and what is the name of this lambda? It's called an eigenvalue. There's some non-trivial vector actually has this property, lambda times V. Is that right? Everything inside here is called eigenvectors. The collection of all these eigenvectors under same eigenvalue is called eigenspace. Make sense? Yeah. Now, book starts with something called invariant subspace. Here's the idea. It's an important idea in mathematics. Invariant subspaces. And decomposition of a linear map. So I want you to underline this term, a linear map. We have some sort of decomposition. Remember what kind of decomposition we had? I give you a vector space. You think about decomposing to direct sum, right? So the same idea, the decomposition, but slightly more involved. And understanding idea is important to understand the graduate algebra, some sort of. This decomposition of linear map, and in it is an invariant subspace important. So it starts like this. We have a gigantic vector space in here, and there is this linear map defined on it. All right? What they wanted to do, they wanted to come up with direct sum of v1, v2. They wanted to split it, smaller pieces. All right? And then you do the same thing. v1, v2. You split it like that. And think about still what this t is doing. Maybe t is sending elements in v1 to v2, right? Maybe sending v1 is element to v1 plus v2. This is not union, right? Remember, v1 direct sum, v2 is not union. Their sum is out there. v1 can go anywhere. But suppose we figure it out very cleverly, the v1, choice of the v1, so if you send all the dt under t, they go back to v1. That's very special, right? If you choose wrong v1, it's all mixed up, but there's right v1 such that v1 goes to v1, the subspace. And also this v2 also goes to v2. So if you restrict this map t to v1, it becomes an endomorphism. So here's, some t1 map. You can restrict under v1. v1 given by all that v1 inside t1 in here, not bar notation here. Go to t, the original map of a v1 for all v1. I'm just going to use v, not v1. It's weird. Inside v1 in here. v1 is the smallest space. If you restrict it, it's not going crazy. It happened to be inside the v1. All right? To them, the mathematicians, this is a great way to reduce the space smaller and kind of separate the map and decompose the map nicely. All right? So if you found such a space, it guarantees that v1, capital v1 is going to back into v1 under the same map that we had before. It's a restriction. But domain is the codomain is also restricted. That's the nice part. All right? If you call this one T1, it's exactly the same formula, but you have a smaller domain and smaller codomain. All right? Why not? Let's keep doing it. So V1 is going to be split further into V12 and V11 and V12. Is that right? Maybe you can do it further. And V2 is a split. It is not a map under T. V2, 1, and V2, 2. And realize it, V1 is not good enough. We can still split this V1 smaller pieces such that the same old map T takes V11 into V11 onto whatever that see what I'm trying to say. So they would keep trying to do this until they can't do it anymore. All right, that is the idea of a decomposition. Right. Just like a prime number, I give you a large number, you try to keep splitting into pieces, eventually it stops, right? That is called irreducible or prime numbers. Okay, here we're going to call the terminology is relative to t. Eigenvector, eigenvalue, those are terminology relative to t, right? So here, if you keep trying to do this, if it's possible, you keep trying to do it, eventually you can't do it anymore. Do you know why it stops? A priori, no reason to stop it if it is infinite dimensional. If it is a finite dimensional, you go down the dimension one at a time, right? So eventually it has to stop. So if it is a finite dimensional, you can see easily it's gonna stop, eventually stop. Finite dimensionality, I put it here, and then I'm going to use new notation. U1, U2, like this, U, let's say M. Each of these has a property that there's no more direct sum decomposition such that is invariant subspaces. These subspaces I'm talking about here, these are called invariant subspaces under T. Does the terminology make sense? It doesn't mean that V is going to V. It's a set-wise invariant, right? Not vector-wise invariant. The whole subspace is turned around, but is not mixed with other subspaces. So this invariant means set-wise invariant, not element-wise, not vector-wise invariant. V1 inside is all twirled up in here, but it doesn't escape V1, is remaining inside there. So we decompose this one into invariant subspaces, right? We keep doing that, and you stop because I can't do it anymore. And these are called indecomposable invariant subspaces. These are indecomposable. All right? So I give you a large space and a linear map, and you think about breaking it down into indecomposable subspaces like this. This is like factoring a large number. So I think I just argued that the existence of a decomposition into what? Indecomposable subspaces is true, provided what condition on V? Finite dimensional. V is finite. It's like integer. You keep factoring and you stop factoring because size is going down every time you factor. Same argument. Inductive argument. All right? So how do we do that? This is the idea, right? Existence idea. But how do we actually do that? One approach, and a very effective approach, happened to be the eigenspace. Right? So here is an example. Column vector is our source of example most of the time. The V is R3. And T is given by this matrix 1, 0, 0, 0, 2, 0, 0, 0, 3. V. Like that. Alright, this is a very special matrix so that you see things clearly. Do you see E0? What was E0? Eigenspace of eigenvalues, eigenspace of value 0, right? This is a determinant 6, right? Determinant non-zero is injective map. Null space must be trivial. So therefore, it's a 0 in here. Do you see E1? E1 is a subspace, and what vector? So I'm going to give you an idea. 1, 0, 0 is E1. What happened if I hit 1, 0, 0 here? 1, 0, 0, that's 1, 0, 0, and you can see this 1, 0, 0, right? So is that, if you plug it in here, you get this one back 1 times V. How about, do you see E2? E2 is a vector, you plug it in here, such that 2 times the vector is spit out. So I'm going to give you the answer so you see if you see that. 0, 1, 0, that's right. If you plug in 0 and 0, you get 0, and second entry is 2, and third entry is 0. You see that? How about E3? Get the pattern? 0, 0, 1. So here's a difficult question. How about E subscript -1? It's not clear here, right? You can't easily conclude here because it's not shown. But that doesn't mean it doesn't exist, right? But the answer is trivial. It's because we found almost all vectors here. There's no more vectors to rule in if you know these are supposed to be the direct sum. All right. So here's the fact that if you just choose any EA and EB, as long as A and B are different, this is supposed to be direct sum. If A and B are different. So if this is non-trivial, then you're going to have direct sum of this thing, all different subscript, right? So dimension 4, but we are inside dimension 3, right? Therefore, no more eigenvalues. Okay? So what we're doing is R3 is, this is going to be the last thing, I'm going to write it down. E1 is a subspace, right? E2 is a subspace, and E3 is a subspace. They already fill up all the dimensions, right? What happened if I hit it with a T? It's still inside in here, right? Inside in E1. What if I hit it with E2? T, still inside in here, subspace, and E2 and E3. You see that? What we just did? What is it we just did in terms of what we've been discussing in here? I split it into invariant subspaces. And why is this indecomposable? One dimension, there's no way to go. One dimension is it, right? If there's one dimension, it's indecomposable. Right? Indecomposable doesn't mean it's one dimension. There's a two-dimensional thing, is cannot decompose it anymore. All right? So this is where the eigenvalue starts. We wanted to look at complicated map and split it into a lot simpler map. If they don't interact, what's the point of looking at complicated map? Completely separate those map. And that's where this one is going. And how do we do this? Eigenvalue is the best way to do it. And that's why develop these techniques about eigenvalues to decompose the map into like this, right? That's what we are entering. Of course, column vector space is a wonderful example, but this advanced linear algebra, you want to do this a little bit more abstract way. All right, I'll stop here.